Okay, we're recording. I'm seeing Mark, Subin's iPhone, Yaxin Lin, Madison Brown, Pablo Gonzalez. Appreciate y'all coming out this morning. Is anybody having any trouble navigating through finding anything in D2L? How did you, I made a video of the assignments where I wrote them out in the video. Is that, was that any clearer?
Yeah, I thought it was a lot clearer. Yeah.
Okay. Did y'all, anybody want to see D2L or where to find stuff in D2L or in WebAssign? Okay, not hearing anything. Did anybody want to see any problems this morning? I don't know if y'all have had a chance to look at this week's work. It's early in the week. We're doing 5.8 and 5.9 this week, or do you still, anybody want to see anything from last week?
Could you maybe work out one of the questions from the quiz?
Which
that you
one?
did? God, let me go open it up. Give me a second.
Okay.
It was number 8, page 362, problem 13.
Page 362, problem 13?
Mm-hmm.
Okay. Yeah, it was pointed out to me that the ebook doesn't have page numbers, but if you go to the exercises at the back of the section in the ebook, the problems there are identical to what's in the book. Let's see if I can find this one. Page 362, problem 13. Okay. It says an integral of x squared minus 7 divided by 7x dx. Okay. As a general rule, if your power on top is bigger than the power on bottom, in the case here, usually signals long division, unless there's only one piece. If I'd added or subtracted something, I would have to do a long division. But with one piece, you can just easily divide out. I'll go ahead and write it out slower. You'd have x squared over 7x minus 7 over 7x. And you can just simply divide out and powers over each other subtract. So this is going to leave you an x divided by 7. Because the x here cancels that one, leaving the x divided by 7. And on the last piece, the 7's cancel, leaving you 1 over x dx. And now things work out piece by piece. On this one, with a 1 there, you're going to add 1 divided by, which gives you 2, and you're going to divide by 2. So in effect, if you want to think of it as carrying along the 1 over 7, and then you get x squared divided by 2. So you're adding 1 to the power and dividing by that. 1 over x is the log plus c. You can combine your 7 and 2, getting 14. X squared divided by 14 minus natural log of the absolute value of x, add c.
Okay, thank you. That's a lot clearer.
Okay, sure thing. Yeah, it kind of shows the difference when your x is on top versus your x on bottom. X is on top, work by power rules, add 1, divide by that. This is the only case that won't work. I don't know if anybody ever pointed this out. Why can't you do that with this? If you have a 1 over x, you can write that as x to the negative 1. Because when you switch levels, you bring it up. If you now try the add 1 and divide by that, you get x to the 0 divided by 0, and this makes the math gods extremely angry. It fails. That's the illegal thing you cannot do in math. One illegal thing you cannot do in math is divide by 0. And so they created the log to handle this situation. You have any other problems you want to see worked out? So integral 1 over x, just to finish it, dx is natural log, turns out. Here's some pages flipping. Anybody trying to find a problem for me to work?
Maybe could you do one of the on page 380, one of the what is it? The thing with the H. So like maybe let's do question 47, sine
47.
H. Yeah.
Page 380,
Yeah.
47.
Mm-hmm.
All right, so in the ebook, this would be 5.9 exercises. And problem 47 there should be identical to this. Okay, I'm seeing integral of a sinh of 1 minus 2x dx. Okay, yeah, this is where I kind of miss my lectures or anything because everybody kind of reading it on their own. I'm not sure what you're getting out of that. I don't know if y'all got that an integral of a sinh is a cosh, and an integral of a cosh is a sinh.
It seems like it's the same as without the H. I'm just confused what the H is. Like I read the book and it wasn't that clear to me.
Sure. Okay, Reader's Digest version. These are called, in 5.9, they're called hyperbolic functions. That's where the H comes from. The H comes from hyperbolic. The hyperbolic. Okay, they are basically combinations of exponentials. The little trig in front of them, like sine H, cosine H, it's because there's a lot of parallels to trigonometry in the sines and everything, and when you take derivatives and etc. But it's not perfect. I'll start with the cosh. The only practical one is this cosh, C-O-S-H. Turns out if you hang a cable between two, it's called a catenary cable. You'd have to do some physics to show this, but you get an equation you can solve, and you will get an answer that looks like this. It's like this combination of exponentials. I can justify it. I hope you remember what e to the x looks like. Directly goes through the y-axis, y-intercept here, dies to the x-axis here. E to the minus x, if you remember, switches around the y-axis. Intercept won't change. E to the 0 is 1, e to the minus 0 is 1. If you add these up, if you take this side and add this, see, this is dying to 0, so it's, this adding this isn't going to change this a whole lot. It still looks up. These are at 1 individually. And if you add on the right side of the y-axis this with this, it curls back up again because you're following this. Your intercept goes to 2. This is e to the x plus e to the minus x. Since they want to bring that intercept back to 1, that's where the divide by 2 comes from. So e to the x plus e to the minus x divided by 2 as this is kind of it's not a parabola, it just kind of resembles one. And they bring the intercept back to 1, so they're dividing this by 2, 2 divided by 2, and bringing that back to 1. That's the only practical application that I am aware of any of this in 5.9. But naturally, mathematicians get a hold of this, and they want to do everything else, because how many other arithmetic operations are there? Well, if you can add these, you can also what? You can subtract them. And then you can divide things. So let me show you the full table. You remember your table of trig functions, sine, they would go sine, cosine, tangent, secant, cosecant, and cotangent. So the table that that resembles your trig, it would go sine of h, and they actually subtract them. Golly, come on. Start fresh. Okay. So what they put resembling the sine, they call it sinh of x, and it's an e to the x subtract e to the negative x divided by 2, even though there's no practical use for it that I have any idea about. The one I just showed you, they call the cosh. Hyperbolic cosine is the full name, and that's when you add them, and it gives you that U-shaped curve. Well, then of course, they wanted something that resembled corresponded to your tangent. So guess what they did? They went sine divided by cosine. Without writing out, this divided by this, you see you'd flip this, the 2's would cancel. You'd wind up with the e to the x minus e to the minus x divided by e to the x add e to the minus x. Does this make any sense?
Yeah, so it's basically like you're using the functions e to the x minus e to the x, like the sine h and cosine h to do all the other trig functions?
Yes.
Okay.
And the sort of strange thing is, even though we're using trig kind of names, this has nothing to do with trigonometry whatsoever.
Basically just trying to give a name to something familiar.
It just has, exactly, and it has parallels to trigonometry. But in other words, if I had you punch a sine of 3, right, you got to pay attention to whether you're in degree mode or radian mode, right? You'll get one answer if you're in degree mode, because that's 3 degrees. You'll get another answer if you're in radian mode, because that's 3 radians, right? I'm not hearing anything.
Yeah.
Okay. Well, if I have you do sinh of 3, and they do have you do this, I don't know if it's the exact one, but they have you do some arithmetic, plug some numbers into these. Well, you get e to the 3 minus e to the negative 3 divided by 2. You can punch it like this because you got an e key. This sinh directly is in the catalog. You can punch it directly. I can show you where it is in the catalog. But does it matter? Do you have to be in degree mode, radian mode?
Nope.
Nope, doesn't matter. Get the same answer either way, because this has nothing to do with trigonometry. So yeah, it gets a little tricky. If you want the other 3, the cosec, hyperbolic cosecant, they just flip it. E to the x minus e to the negative x. The hyperbolic secant, the SECH, 2 over e to the x plus e to the minus x, and the hyperbolic cotangent, coth you could call it, e to the x plus e to the minus x over e to the x minus e to the minus x. Even though, again, I have no idea what any practical application of any of them are. Let me just show you, if you then, where the parallels come in is if you wanted a derivative of the sinh, you would take a derivative of e to the x minus e to the negative x divided by 2. You would get e to the x, derivative e to the x, e to the x, minus, and you'd get e to the minus x, but with a chain rule of -1, divide by 2, and you get e to the x add e to the minus x divided by 2, because these two negatives turn positive, and that is directly your cosh. So the parallel exactly works. Derivative of sine is cosine. Derivative of sinh is cosh. Did that go through that too fast?
No, yeah, that made sense to me. Yeah.
Okay. The problem is when you go backwards, it fails. Try derivative of cosh. So you'd go a derivative of e to the x add e to the negative x divided by 2. So you would get a derivative of e to the x plus e to the negative x, but with a chain rule of -1. Chain rule from up here, -1, divide by 2. Well, that makes derivative, I'm sorry, that is, no, that is, I'm sorry, this is your derivative. I should have dropped the derivative symbol. This is your derivative. That means you get e to the x subtract e to the negative x divided by 2. And guess what? That is exactly your sinh.
Sinh.
In other words, golly, not writing well today, sinh of x. So in other words, there's no sign flip. Derivative of cosine is negative sine. Derivative of cosh is a positive sinh. So it isn't a perfect analogy.
Okay, that makes sense. Okay.
This means that they roll over on each other when you do derivatives. Derivative of sinh is a cosh, derivative of cosh is a sinh. And also when you do the antiderivatives, they roll over on each other, but of course you add a plus c. So in other words, integral of a sinh is directly a cosh. But don't forget your plus c, because you're always off by a number. And your integral of your cosh is your sinh. There's no sign problems, plus your c. All right, that's why there is it. Whereas if you did it with trig, there's a sign in it, depending on which direction you're going.
Yeah, that makes sense.
Cosine be like a negative sign, I believe.
So it's just one of those things to like, if you aren't doing like the math out, it's just something to remember, kind of.
Yeah, just kind of remember. Yeah. Back to your problem. With that introduction, you want to try your problem again? It was 47.
Yes.
Okay, you're going to have to bring a u du in on it. You take an integral of a sinh of 1 minus 2x. All right, you want to get it back to this form right here with a single letter. That makes this your u. You will then need to do a du -2 dx. So you're going to have to slide a -2 in here, fix it with a -0.5 in front. So you'll have an integral, I'll keep it in x one more step, with a -2 dx. This will form your du. This will be your u. You will need a fix of a -0.5 in front. So that gives you a negative a half, an integral of a sinh of u du. Have we paused for station identification? Have we lost anybody?
I just have a question.
Yeah.
Isn't the integral of sine of x negative cosine of x plus c?
Uh-huh.
Then why did you put cosine of x on?
See, that's a difference between cosine and cosh. See, sine, cosine, tangent are trig functions, and they have their own rules. They've made these functions up. They're combinations of exponentials. They have nothing to do with trigonometry. And that's what I was trying to show you on the previous page. Their signs can work a little differently.
Oh, I
You want me
see
to-
now.
Go ahead.
Never mind, I got it now.
Okay. So then this integral directly matches this one up here, just in letter u, not x. So this integral works out. You got a negative a half, a cosh of u plus c. And finally, you put back for the u, and the u was 1 minus 2x. Negative a half, cosh, 1 minus 2x plus c. Cosh, I lost the h, I'm sorry. Yeah, don't lose the h, it's easy to do.
So
Cosine
basically,
and cosh are completely different animals.
so everything basically goes back to just like trying to get it into a form you can integrate again. So like using
Yes.
the u. Okay.
That is correct.
When we take like the proctored test, are we going to have an integration table, or do we have to memorize all those?
I will give you a review sheet for the test. The review sheet will have the formulas or the integral forms that I don't expect you to know. And so on the actual test, you will have that same formulas or integral forms. Does that help?
Yeah.
Someone emailed me in and wanted like 2 or 3 problems worked. Trying to pull it up. Oh, gone, where'd that thing go? Okay. Yes, she wanted 17, 21, and 35 out of 5/8. Now, does anybody here have, I don't believe she's here in the meeting. Anybody have anything else you all want worked? Because I'm supposed to work these 3 problems for her in this meeting. Or do you want to see her problems?
I want to ask a really quick question.
Yeah.
I know we learned 5.7 and 5.8, and how I know when because I'm kind of confused. Sometimes I think I should use log function on 5.8. Like I don't know when I don't know when should I use the trig function or when should I use the log function.
Can you give me an example?
Because how about that? Let me give you a page number. We have exercise 362 and 370. Page 362 and 370.
Right.
Both page, I think the topic is stating that find the indefinite integral.
Right.
And 5.7 pretty much you just write log form. And 5.8, which is like, we use the trig function form, sine, cosine.
Right.
How in the test, how I know which one should be used which?
Yeah, you
I don't want to put a log form on the trig function.
Right. Okay, 362 that was 5.7, right?
Yes. You know what I try to explain?
Yeah. Okay, this is 5.7 log forms.
And 5.8 is trig form.
Right, but page 370 was 5.8, which was trig forms, right?
Yes.
Okay.
If there's a problem showing up, how I know I should use log form or trig form?
Okay. Log forms come up with linear terms on bottom. In other words, I'll write out a few examples. Straight 1 over x is a log. Now, you can add or subtract something here, and it really doesn't change a whole lot. 1 over x plus 3 is a log of x plus 3 plus c. You can subtract something, doesn't change anything. Where you get problems is if you put coefficients or powers. So for example, let's say I put a 1 over 2x plus 3. All right, can you tell it can't be a straight log of 2x plus 3. You see, when I do a derivative on this, the check, derivative of log of x here is 1 over x. Derivative of log of x plus 3 is 1 over x plus 3. But you see, if I write this as log of 2x plus 3, and I do a derivative 1 over 2x plus 3, yeah, it's here, but you see there's also a chain rule of 2. Do you want to see how this one actually works correctly? It's not this. I'm losing you. Is this making sense or?
Yeah, it's making sense. I think allows the linear term on the bottom, which should be good on log form, right?
Right. You want a linear
And we
term?
can
Yep.
and we can check after find log form, and we can derivative it back to make sure it's the right answer or not.
That's right. Do you want to see how this one works correctly?
Go ahead, please.
You would use a u, do a derivative and get a 2. So then you would plug it in as integral 1 over u. Maybe I should have written out one more step. You would do 1 over 2x plus 3, put a 2 dx from here, fix it with a 1/2. Now you get a 1/2 integral 1 over u and du. See, this is your u, this is your du. And now you have your linear term on bottom, but in letter u. So you're following this form, but in letter u. Making 1/2 log of u. And you don't have to write the absolute value. It just means that your input has to be positive. You leave off the absolute value, I won't mark it wrong. And so that gives you a 1/2 log of 2x plus 3 plus c. So that's why you can't have a straight log here. The chain rule come out would be a 2 when you do a derivative, which is not here. This u du gives you that 1/2, which cancels your 2 from the chain rule here. In other words, your derivative here would be 1 over 2x plus 3 with a chain rule of 2. That's canceled by this 1/2. Questions about that?
I think we good
Okay. Do you want me to compare it to the 5.8 trig forms?
because the question I really want to ask, at the beginning is how I know if, for example, in page 362, question 11,
Okay.
and I think if like I thought this might be a sine form instead log form. That's why I kind of confused when so I use the form.
Okay, I can show you the sine forms out of 5.8. They'll all have well, two of them have a square root and one of them is not a linear. I can compare them and show you why. But do you want to see problem 11 worked on page 362?
No, I got a 362. The only question I got is I don't know when to use the log form, when to use the trig function form.
Okay, well, let me show you why you don't use the trigs on this, on problem 11. See, in 5.8, there's three really arc trig forms. Form number one, an integral of 1 over the square root of 1 minus x squared is an arc sine. Okay. This is not a linear term on bottom. It doesn't look anything like this. And problem 11 doesn't look anything like this. The second form is the an arctangent. An integral of 1 over 1 plus x squared is an arctangent. And the third one's the arcsecant. We put an absolute value of x, square root of x squared minus 1 is an arcsecant. Now, some Calc 1s cover this and some don't. It's tough to derive all three for you. Is this old news? You've seen this before? Or is this like, whoa, I've never seen this before?
I think in Calc 1, I learned integral, but we didn't go that far yet, I think.
Okay.
But I'm comfortable with integral what we do in Calc 1.
Okay. Well, you see, none of these look anything like an integral of 1 over x.
Yes, I think I got it because they got square root.
Right.
And I think I know how to make the difference between when to use sine, cosine form.
Okay. This is, I guess, where I miss doing a regular lecture in a classroom, because somebody might be out there going, whoa, what is that? I can derive one of them. The first one's pretty easy to derive. Anybody want to see it derived? It means another page of gibberish deriving it for you. And then the other two are pretty similar. Anybody interested in that, or would you rather just see problems worked?
I would like to see that, please.
You mean you actually want me to do my job?
Yes, sir.
Wow, okay. God, why did I offer? Let me see if I remember how to do it. Because it's probably been 10 years since I've taught Calc 1. Okay, this is going to bring in a lot of skills from trigonometry. In fact, let me just go through a couple of them just to see if you remember this. At some point, we're going to wind up with a triangle, and we might have an X and a 1 here. Do you know or remember how to get this other leg? We'll just call it U for an unknown. X squared plus U squared would equal 1 squared. You know, Pythagorean theorem, leg squared plus leg squared is hypotenuse squared. Your U squared would be 1 minus X squared. And your U would be the square root of 1 minus X squared. This ring a bell?
Yes, sir.
That ring any sort of bell from trigonometry?
Yes, sir.
Okay. Okay, we're going to need this, something like this in the middle of this. I just wanted to remind you of it when it comes up, so it won't look like total gibberish. All right, let's derive that the integral of 1 over square root of 1 minus x squared comes up in arc sine. You basically to show this, do a derivative on both sides. And the derivative c goes away. So then this cancels, and basically it means that a derivative of arc sine is this, that a derivative of arc sine of x is equal to 1 over the square root of 1 minus x squared with no chain rule. Make this say anything other than an x, and you'd start with this and tack on whatever the derivative of this is for a chain rule. All right, so it's really equivalent to showing this, that I can differentiate an arc sine and come up with this. All right, start with, we'll call this y. Y equals arc sine of x. Take d dx, both sides. You may regret asking this after you see, but I'll do my best. Like I say, all three of them would be overwhelming, but that means you're going to get d dx of y is d dx. No. I'm jumping through. I'm one step ahead. Take sine y. Sine y is equal to sine of arc sine of x. And that means sine y equals x, because these invert. Now take d dx, both sides. d dx sine y equals d dx of x. Okay. Calc 1, they talked about something called implicit differentiation. Can't, like say, reteach that whole thing. Bottom line is, if the letters match, this is derivative of x with respect to x, it works by the same rules. This is a simple 1, because the coefficient is 1. But when your letters don't match, you have to throw in the chain rule, because this is in effect an unknown function. So it's going to work by sine. Derivative of sine is a cosine of y. But you see if that's an x, you're done. That's cosine is sine x, so that's a cosine x, and you're done. But it's not. It's the letter's different. That means you got to tack on its chain rule, which is a dy dx. I'm going to go to the next page and solve for dy dx, which means I divide by cosine y. Let me rewrite the line and I'll show that. So I've got cosine y, dy dx equals 1. Divide by cosine y, dy dx, 1 divided by cosine y. What? Yes. Yes. It's probably Mr. Shadburn. Okay. If you remember from the beginning, y was arc sine x. So let's d dx, arc sine x is 1 over cosine of arc sine x. Okay, I've had someone come to my door. I've got to go down and, no, okay, let them figure it out. Okay. So this is what I'm trying to figure out, and it's equivalent to working out this. This is where you need your triangle. The angle is an arc sine x. Put it over 1, and it means your x is opposite and your 1 is 1 is on the hypotenuse. It's opposite over hypotenuse. Okay, this is where, do I need to redo the algebra again? You would get a square root of 1 minus x squared. The other example I did, I stick the x down here and you get this. You get the same formula for the leg no matter where it is. And now your cosine of this on the triangle, cosine is adjacent over hypotenuse, which is the square root of 1 minus x squared over 1, which is a straight square root of 1 minus x squared. And that goes in right here on bottom, meaning d dx of arc sine x is 1 over the square root of 1 minus x squared. And if I do an integral on both sides, these again cancel, and there's my integral of 1 over the square root of 1 minus x squared is equal to my arc sine x plus c. I don't know if that proved anything to anybody, but in any case, that's how you show it. And the other two work pretty similar. Can I ask for a 2-minute break? I've had a workman come to my house. I need to go down and see what they want. 2-minute break, and I'll be right back. I apologize for this. I wouldn't do this ordinarily. I'll be right back. Do I need to do anything? Okay, I apologize. Break is over. Did that prove anything to anybody or only to me? Is
No, I
anybody
got
still
it.
there?
I'm here.
Did that prove anything to anybody?
Yes, sir. Thank you.
Okay. Well, again, the other two forms, you can do a really similar thing and show them. But the other two forms, I'll rewrite them again. Is an arc sine and no square root, and there's a plus sign. This comes up a lot. Is an arc tangent. And then the arc secant doesn't come up very much, but they put it in. Your letter goes first. And you have a letter goes first under this. Got square root, your letter goes first. Got an extra x in front. Oops, I'm not showing this real clear. Is an arc secant of x plus c. Does anybody want to see an example problem worked?
Yes, please.
Okay,
Sure.
you want to pick one out?
Wasn't there someone that wanted you to do some problems, so we can do one of those?
Okay, she wanted 17, 21, and 35. You want me to charge into those?
Works for me.
All right, let me look. These are off page 370. they're further down the page. Let me try to just show a really simple one. I like to show simple ones first to try to get people warmed up. But let me just start with the first one, which is number 3. And it's an integral dx over the square root of 9 minus x squared. Okay. I can write out a whole bunch of steps, or I can do this the simple way. Which would you prefer? Really complicated or really simple?
Bunch of steps.
You prefer the bunch of steps?
Why?
Oh, I thought you meant like you're gonna write it out more, like explain it a little bit more.
Well,
That's what you meant.
Why we not just make life easier?
why make life easy when we can do it complicated? Okay. Notice how the basic form has a 1. This has a 9. Now I could write out a whole bunch of steps and show you how to convert the 9 to a 1, and so that you can eventually use this form, etc. But the easy way look on page 365. This is actually the first page of the section. And they give you more general forms. In other words, they give you a general number for the 1. They use an a. A squared minus u squared. They switch the letter to u. Don't let that bother you. That's an arc sine of u over a. So in other words, you've got your number first minus your letter squared, and it turns out it gives a coefficient, or puts the u over the a. I could again take another page and show you why, but I'm trying to, like I say, compress this. Turns out there's a slight difference when you do the arctangent. That's form 1, say. Form 2, when you do an a squared plus u squared, again, these are still off page 365, it gives you a 1 over a coefficient with an arctangent of the u over a. And if you do number 3, 1 over, you get an absolute value of u, again, they're switching to letter u, square root, put the letter first, u squared minus a squared du. You also get a 1 over a on an arcsecant. Okay, if you just follow these forms, this makes your a appear 3. A squared is 9, a would be 3. It's got the number first minus the letter squared. That means you just simply get an arc sine of x over 3 plus c. Write it right down in one step. Or I could do an entire page demonstrating why you get the x over 3. Question about that? Okay, doggone, we're at 50 minutes. Let me see if I can work some of her other problems here. This may be a long one to upload. It was 17, 21, and 35. 17, 21, 35. They're off page 370, wasn't it? Okay, 17. Integral 1 over square root of x, square root of 1 minus x dx. Okay, you're going to get a similar pattern on a lot of these. to use these trig formulas, notice how it's got the number first and then the letter. It might remind you, got a piece outside, which might say arcsecant, but then again, it might get taken care of and become an arcsine. I haven't looked at the answer. But what you want to do to use those forms is put a square here. So that means u squared equals x. You take a square root and get u as the square root of x. And you want a derivative on that. Remember, that's in a half power. 1/2 x to the negative 1/2 dx. We can play around with that. 1/2, 1 over square root of x dx. So last sections, we just started with u and a du. These sections, I like to write down the initial step if I need it, that you plug in a u squared. All right, let me rewrite the 1 over square root here to the back to make it more obvious. Square root 1 minus x, 1 over square root of x dx. This is going to form my du, but I do need a 1/2 in it. Therefore, at the front, I need a 2. And this is my u squared. So I wind up with a 2 integral 1 over square root 1 minus u squared du. I guess we'll pause for station identification. Did anybody want to ask about anything? I don't know if y'all are still with me or not. We're getting really long. Maybe y'all have abandoned me. That's fine. Anybody still there?
Yeah, I'm following.
Okay. Well, that is your straight arc sine in u. So this is twice arc sine u plus c. And your u, from right here, the middle line, was the square root of x. Twice arc sine square root of x plus c. This kind of pattern on the substitutions is going to occur a lot in this section. Start off with u squared, then a u with a square root, then the derivative du. And then you sub in. And it should work out one of those three forms, an arcsine form, arctangent form, or arcsecant form. Is this enough on this one? You want to go to 21?
Yep.
Okay. Integral, again off page 370, 5.8. X plus 5 over square root of 9 minus x minus 3 squared dx. Same idea. You want to get a single letter squared there. So that tells you how to start. U squared, x minus 3 squared. Square root to get u. Derivative is simply 1 du. Du is simply 1 dx, or du equals dx. No fix needed. Du and dx are identical. This is du. Okay. We just have to account for this x up here. If you look at this line, if I add 3, u plus 3 is equal to x. You have to kind of be able to do whatever you need to do to sub in and replace all the pieces. And every problem is a little different. That's what makes this course so tough. So for that x, I'm going to stick u plus 3. Still have the plus 5. Bottom, I still have square root of 9 minus u squared. Dx is du. This gives me an integral u plus 8 over square root of 9 minus u squared du. It looks like an arc sine here, but you've got multiple pieces. Whenever you see that, that's a signal to break it up. Square root 9 minus u squared plus, I'm going to throw the 8 out. You could have left it in. 1 over square root 9 minus u squared du. Reason for throwing it out, it might look, this is a direct arc sine form with an a of 3. You remember, therefore, this is going to give you a plus 8 in arc sine of u over 3. So you've got the 1 there. You can't do a u du on this because your derivative, if you make a quote u, your bottom, your derivative is a 2u. There's no 2u here. This, with a u here, is not an arc sine. If you want to see the pieces written out, this is going to work out by u du, but we can't use letter u because we're already using it. Maybe I'll use a. A equals 9 minus u squared, and dA is negative 2u and du. So this works into an integral of, I need a negative 2 and a negative 1/2 for the fix, so I need a negative 2 in, fix it with a negative 1/2. I'll get a 1 over the square root of a dA. This one's kind of a long one. That's an a to a negative 1/2 power dA. I'll carry along my 8 arc sine u over 3. I think I remember telling y'all some of these go 2 substitutions deep, and here we are. This is your second substitution. So this works by adding 1 and dividing by that. Means I get an a to a 1/2 divide by 1/2 plus my 8 u over 3 plus c. That 1/2 flips around to a 2, a to 1/2 plus 8 arc, oops, I'm off the page, 8 arc sine u over 3 plus c. I got room maybe for one more line in u, so I get this back to u, replace the a with 9 minus u squared, so that's a twice 9 minus u squared to 1/2 plus an 8 arc sine u over 3 plus c. One more move and I'm out of this page. So on the next page, I'm going to stick in for the u, and the u was x minus 3. U was x minus 3. I've got twice 9 minus u squared to 1/2. Add 8 arc sine u over 3 plus c. Double check that is what I had. I memorized it. Yep. And finally putting back that u is x minus 3 twice x minus 3 squared, 2.5. Add 8 arc sine, divide by 3 plus c. Now, this is perfectly acceptable, but it's probably not what you're going to find in the back of the book. This piece should be there because you can't really simplify that. My guess, the back of the book foils this out, distributes the minus sign through, brings in the 9, and converts that to whatever formula you get. But you don't have to do that. I'm getting the mood of the room to put a whole bunch of those on the test.
No, please.
Okay. Always misread the mood of the room. Dead gum. Did anybody want to ask anything about that before we do the third one? I think it was 21. No, that was 21. The third one was, I don't remember. Did anybody want to ask about this one before we do the third one? Doggone, we're at an hour. It's going to take forever to upload. The third one was, anybody have it? I don't know if I can find it. 35. Third one was 35. Anybody want to ask about 21 before we jump on to 35? No, are we ready for 35? Okay, 35 with numbers can be just punched in on the calculator. Integral from 0 to 2. X squared minus 2x add 2. If they give you numbers, use Math9 on calculator. I'm not going to show you how to work it out by hand. I'll write out what you get when you hit Math9. Now you may have the interface that it looks exactly like this. All you got to do is fill in the pieces. So it might give you a box here, a box there, a box for the formula, a box for the x. It'll look exactly like it's written on paper. I've got the old interface, so mine comes up function integral. First thing is my formula. I'm going to go 1 divided by parentheses minus 2x add 2, close, comma. I put an x for the dx, comma. My lower limit is 0. My upper limit is 2. I should get one of the new fancier interfaces. Let's see if I can read that. So let's see, clear off math. Math is right there. 9, function integral. 1 divided by parentheses. X squared, the x is right here, just like your graph, squared minus 2x plus 2, close, commas above 7, I put an x for the dx, comma 0, comma 2. If I can make it any better, bring it up a little closer. And it's the very old interface. When I hit enter, 1.57, that smells like pi over 2. That's the easy way to do problem 35. And this is the way we're going to do them all when they have numbers. We're not going to work them out by hand. You have to get an antiderivative, then plug in the 2, plug in the 0, and subtract. We're not going to do those that way. Not when we have access to a nice machine. We are an hour and 5 minutes. Did anybody want to ask anything or say anything before we close the meeting? Ask any questions about these problems or? I don't hear anything. Are we ready to end the meeting?
I'm all good.
Okay. plan the next Zoom meeting for Friday at 9 a.m. So I appreciate if anybody stuck it out. Looks like at least one person stuck it out this long. Really appreciate you hanging around. And we'll see you again. You can, of course, ask me any questions you want by email between now and Friday, and we'll do another Zoom meeting Friday at 9 a.m. Thank you very much. We'll end the
Thank you.
meeting.
Thank you. Have a good day.
Thank you.